Hey guys, my name is IBM and I'm taking you through quantum physics. These lessons are designed for my students, so if you don't find them useful, there's no problem. I just expect that my students will find them useful and they will help them to always revisit in case they miss school or in case they miss a class. This is going to be lesson 5 of quantum physics, and I think in lesson 5 I'm going to introduce the energy levels in atoms and the line spectra. Okay, so let's go. Energy levels and the line spectra, that is what we're going to talk about in lesson 5. So just to remind ourselves of the atomic structure, I want to remind you of the atomic structure you mentioned in AS physics. You talked about Rutherford's mode of the atom. So in 1911, after the famous alpha scattering experiment, Ernest Rutherford proposed that the positively charged electrons revolve at a high speed in circular orbits around a nucleus. This led to what we call the planetary model, that electrons revolve around the nucleus in the same way planets revolve around the sun. So in AS physics, you described the nuclear model of the atom in more details, and you mentioned that an atom is entirely a positively charged nucleus with the negatively charged electrons that were revolving around the nucleus. Of course, this was after the failure of the J.J. Thomson's model of the atom, and the nuclear model of the atom was adopted or was considered to be better than J.J. Thomson's plum pudding model of the atom. However, this planetary model, this model according to Rutherford, also has some setbacks or drawbacks. According to the classical electromagnetic theory, if a charged particle were accelerating around another charged particle, there would be a continuous radiation of energy. If electrons were moving around a positively charged nucleus, as suggested by the nuclear model or Rutherford's model, then we would expect, according to the classical theory of electromagnetism, we would expect that electrons, which are negatively charged, in revolving around a nucleus which is positively charged, the electrons would lose energy. So this loss of energy would slow down the speed of the electron, and we believe that uh, it would eventually collapse into the nucleus. Unfortunately, this does not happen. Electrons do not collapse into the nucleus. Yet, classical theory of electromagnetism predicts that whenever a charged particle is accelerated around another charged particle, it loses energy. If electrons were to lose energy, they would collapse into the nucleus. This would suggest that we would have unstable atoms around us, and therefore we would have unstable matter around us. Unfortunately, this does not happen. The electrons do not collapse into the nucleus, which means we have stable atoms around us, or matter is made up of stable atoms. So Rutherford's model does not explain this stability of atoms. Such a collapse does not occur, and Rutherford's model was unable to explain why the collapse of electrons into the nucleus does not occur, or why we have stable atoms around us. So this means this model was also not sufficient. Rutherford's model was also not sufficient, and therefore another model had to be adopted, and that is going to be called the Nail-Bors model, or the Nail-Bors atomic model. So we started with J.J. Thomson's model in AS physics, particle physics. It was discarded. We adopted the nuclear model according to Rutherford and his colleagues. It is now being dropped because it does not explain the stability of the atom. Not only that, it also does not explain the line spectra that we are going to establish later on. Okay, so let's now adopt a new model therefore because J.J. Thomson's model has now failed. Around 1913, the quantum theory of Rutherford's, around 1913, Niels Bohr in 1913 applied the quantum theory to Rutherford's atomic model, and he proposed that electrons travel in stationary orbits, or electrons travel in only certain allowed orbits, which we shall call stationary orbits. His argument was that when electrons are in these orbits, they do not emit radiation. So electrons move around the nucleus as it had already been proposed by Rutherford. However, Niels Bohr is suggesting that unlike Rutherford, who never explained why electrons do not collapse into the nucleus, for him is arguing that electrons revolve electrons revolve around the nucleus in only certain allowed orbits, and these certain allowed orbits are what we are going to call stationary orbits. These orbits are defined by what we call angular momentum, or by their angular momentum. We shall not go into the details of what we mean by angular momentum at this level, but at least we know what we mean by linear momentum from AS physics. So these stationary orbits, or these allowed orbits, led to the calculation of possible energy levels for these orbits. If there exist only certain allowed orbits or only certain stationary orbits in which electrons revolve around the nucleus, and Niels Bohr suggested that while in these orbits the electrons do not emit energy, then several calculations had to be carried out to come up with these possible energy levels or these possible stationary orbits. So Niels Bohr postulated that emission of light or emission of electromagnetic radiation only occurs whenever there is a transition. In other words, whenever an electron moves from a higher energy level, or from a higher stationary state, or from a higher stationary orbit to a lower stationary orbit. But if an electron does not make any transition from a higher stationary orbit to a lower stationary orbit, then no energy can be lost, as the classical theory of electromagnetism would predict. So Niels Bohr is simply uh, explaining what Rutherford did not explain. He did not suggest a concrete new model of the atom. However, he gave an explanation which Rutherford did not give to account for his model. He is suggesting electrons travel in in stationary orbits, or electrons travel only in certain allowed orbits around the nucleus. Rutherford did not specify this. For him, he just suggested electrons revolve around the nucleus. And we notice that electrons are negatively charged and the nucleus is positively charged. And according to the classical theory of electromagnetism, whenever a charged particle is accelerated around another charged particle, it loses energy. And if electrons were to lose energy, we would see them collapse into the nucleus. But because this does not happen, and then Rutherford did not explain why it doesn't happen, then his model had to be discarded. Then Niels Bohr just simply explained why electrons do not collapse um, into the nucleus, and he suggested, or he proposed, that electrons only travel around the nucleus in certain allowed orbits that we are now calling stationary states. While in these orbits, the electrons do not give out energy. Therefore, while in these orbits, there is no emission of light. While in these orbits, there is no emission of photons. And therefore, the electrons remain with their energy and continue moving around the nucleus in those allowed orbits. However, he argued that if only an electron makes a transition from a higher energy level to a lower energy level, that's when the electron would emit energy, according to Niels Bohr. So, electrons are therefore orbiting the nucleus in only certain allowed orbits. So, these electrons can only occupy orbits, which orbits have integer values of n. So, an electron can only exist on certain orbit where n is say equal to 1, n equals to 2, n equals to 3, but this electron cannot exist between n equals to 1 and n equals to 2. It is either on n equals to 1 or on n equals to 2, not anywhere in between. So n equals to 1, n equals 2, n equals to 3 are going to be called stationary orbits. And while electrons are in these orbits, according to Neil Bohr, they do not lose energy. However, if an electron makes a transition, say from a higher energy level to a lower energy level, that's when it gives out a photon of energy. That's when it gives out light. So Bohr postulated that emission of light or emission of photons only occurs when electrons move into a lower energy orbit. So whenever a photon makes a transition, that's when it emits light, or that's when it emits a photon. Okay, so to explain this in more details, we are saying that electrons can move only in certain allowed orbits around the nucleus. Both circular orbits, we have already called them stationary states. These ones, when in these states, electrons do not give out energy. So electrons in these states therefore behave very much like stationary waves. If you remember stationary waves, think of a stationary wave which is fitted into the circumference of the orbit. That means if it is fitted into the circumference of the orbit, the circumference is 2 pi r. And of course, when we have a stationary wave being formed, we have interference of waves and 2 pi equals to n lambda, where r is actually going to be now the radius of the orbit. Lambda is going to be the wavelength of the electron wave, because we are assuming that the electrons are moving around the nucleus in what we are calling stationary states, and they are behaving as if they are stationary waves which have been fitted into the circumference of the orbit. If you recall your AS physics, stationary waves do not transfer energy. Similarly, when electrons are in these stationary states, they do not give out energy at all. So the circumference, which is 2 pi r, is going to be equal to n times lambda, where n therefore is going to be equal to it is going to be equal to an integer which is called the quantum number of the orbit. That is, if the electron resides on an orbit where n equals to 1, then it means the circumference 2 pi r of the electron wave is just going to be equal to the wavelength. And when we move to n equals to 2, it also means that the radius of the orbit must have increased. So r is actually the radius of orbit, lambda is the wavelength of the electron, and n is the integer that we call the quantum number of the orbit. Okay, so we therefore conclude that electrons can only exist in what we are going to call stationary states, that is for n equals to 1, n equals 2, n equals to 3. But electrons cannot occupy states between n equals to 1 to n equals 2, for example, n.1, n equals to 1.1, and so on and so forth. So these are going to be called stationary states. However, an electron can cross from one state to another, as given by the second postulate. Electrons in each orbit have a definite energy. The energy is definite, and they move in that orbit without radiating energy. So while moving in the stationary state or in the stationary orbit, electrons are not expected to give out energy. The energy will only be given out when the electrons make a transition. So if we consider a free electron is the one which is actually at infinity, because that should be at n equals to infinity. Of course, we know that as electrons get closer to the nucleus, if they get closer to the nucleus, they lose their energy. Therefore, it means from electric fields, we said potential energy is electric potential is maximum at infinity. So a free electron at n equals to infinity is the one which has zero electric potential energy. So an electron must be given energy to reach infinity, and that electron will have maximum energy, which is going to be zero. That means between the nucleus and infinity, the energy or the electric potential energy is supposed to be negative, as we mentioned in electric fields. Maybe to understand Bohr's postulation or to understand Bohr's mode of the atom, let's try to watch an animation. I don't know whether it will show. Okay, so using this animation, we are going to see what Bohr was trying to postulate. So Bohr was postulating that electrons revolve around the nucleus in only certain allowed orbits. So in this animation, we have 1, 2, 3, 4, 5 orbits, and an electron, which is the black spot, continues to move in that only orbit. So I'm going to give this electron some energy. Let's say I give it energy. When I give it energy, it moves to a higher energy level. I have given it energy, so it has moved to a higher energy level as indicated by this animation here. Of course, we notice that when an electron in an atom gains energy, it becomes excited. It becomes excited. And it doesn't stay there for long. That's why you see it has jumped back to the lower energy level, which we are going to later on call the ground state. In the ground state, the electron is going to continuously move in that orbit, and the atom is going to be stable. But when I give it energy and the electron moves to a higher energy level, the atom is going to be said to be unstable. So it will not take a long period of time there before moving back to its ground state, because in its ground state, the electron has the lowest amount of energy and the atom is going to be stable. However, I want us to see what happens when an electron makes a transition from a higher energy level to a lower energy level. So moving from the fifth to the fourth, every time the electron makes a transition from a higher energy level to a lower energy level, you see that there is emission of light or there is emission of electromagnetic radiation, which means, according to Neil Bohr, whenever there is a transition, an electron will give out the excess energy which it has acquired or which it had, so as to make the atom to become stable. So whenever there is a transition from a higher energy level to a lower energy level, the atom gives out some of the energy it has acquired. But if there is no transition, the electron continues to revolve around the nucleus in that orbit, and that orbit is called a stationary state. If I give this electron more than this is 13.98 electron volts. This is more than the energy an electron in a nucleus or in a hydrogen atom requires to move to infinity, because the minimum energy it requires is about 13.6 electron volts. So if I give the electron 13.98 electron volts, the electron is going to move to infinity. Therefore, we shall not see it in the orbit. So the electron is given excess energy and it moves to infinity. So this animation just demonstrates what Neil Bohr was trying to postulate. Electrons revolve around the nucleus in only certain allowed orbits, while in these orbits, they do not give out energy. If an electron is to give out energy, or if an electron gains energy, like I've given this energy, it moves to a higher energy level. If the electron moves to a lower energy level, it goes on emitting energy, as you can see in this case. As it moves from 3 to 4, 3 to 2, it gives out energy, and 2 to 1, it gives out energy. So that is Neil Bohr's postulate. Okay, so having seen Neil Bohr's postulate, we can now go to an understanding of this postulate in more details. So I said a free electron is the one which is having n equals to infinity, and it has gained excess energy so that it is free to break from the attraction force between itself and the nucleus. So it is at infinity, we say it has zero electric potential energy. And if the energy at infinity is zero, it means all energy levels between infinity and to the nucleus, in between infinity to the nucleus, all energy levels are going to be negative. This means that when an electron moves to infinity, it gains electrical potential energy. And when an electron comes closer to the nucleus, it loses electric potential energy, simply because for a positively charged nucleus and a negatively charged electron, this is a positively charged nucleus, and we have a negatively charged electron. The force on the electron is attractive towards the nucleus. So moving the nucleus, so if the electron moves towards the nucleus, it is just losing energy. But if the electron moves away from the nucleus, it is moving away against the force of attraction. Therefore, we say it gains electric potential energy. So if an electron gets closer towards the nucleus, it loses electric potential energy. So the energy at n equals to 1 is the lowest potential energy, and this is called the ground state of the atom. The ground state of a hydrogen atom, for example, is minus 13.6 electron volts. The ground state is minus 13 electron volts. Historically, n equals to 1, or in chemistry, n equals to 1 has the quantum number 1, which in chemistry I think you call the K shell. So the smallest or the lowest potential energy in a hydrogen atom is negative 13.6 electron volts, which means if at infinity, where n is equal to infinity, the electric potential energy is 0, and yet at n equals to 1, which is the ground state, the electric potential energy is negative 13.6 electron volts, which means to send or to make an electron to leave the nucleus, to move to infinity, or to make an electron to be completely free from the nuclear force of attraction, then it needs an energy which is the difference between those two values, which is 0 minus negative 13.6 electron volts, which is 13.6 electron volts. That's why you notice that in the animation, when I gave the electron an energy of 13.98 electron volts, it simply escaped from the orbits. It simply went to infinity. So the ground state of the hydrogen atom is approximately minus 13.6 electron volts. I'm not supposed to derive this energy, but in another curriculum, that energy can be derived. Okay. So what are these electron energy levels and the line spectra? We know that when white light is incident, or when white light passes through a prism, the white light undergoes what we call dispersion. It splits into its 7 constituent colors that you saw in IGCSE physics. When white light goes through a prism, the white light splits into its constituent colors, the 7 colors of the rainbow. And when you clearly look through these colors, you notice that there is no clear boundary between red, orange, yellow, green, blue, indigo, and violet. There is no clear boundary between these colors. This spectrum of colors, of these 7 colors, which actually overlap, red simply fades as violet comes in, even though here it appears as if there is a boundary. But in the real sense, there is no clear boundary between these colors. This kind of spectrum is what we call a continuous spectrum, because there is no clear boundary between the 7 colors. So this band of 7 colors, this band of different colors, we call it a continuous spectrum. Since it has all the colors, when I talk about the colors, each color represents a wavelength. It has all the colors between two limits. The limits are red and violet. The color and wavelength limits are violet, which is around 400 nanometers, as you saw in AS physics, and red, which has about 700 nanometers, as you saw in AS physics. Since this spectrum has been produced by the emission of light from the tungsten filament, which I mentioned here, it is referred to as an emission spectrum. So the 7 colors, when passed through a prism, they form the white light, when passed through a prism, it forms a band of colors where there is no clear boundary between one color and the other. Therefore, this band of the 7 colors is called a continuous spectrum. It is called a continuous spectrum. If we want to get finer details, for the light coming from a tungsten filament, so finer details of emission spectra a finer detail of emission spectrum than this obtained using a prism may be achieved using what we call a diffraction grating that you saw in AS physics of waves. So white light is split into its constituent continuous spectrum when it is also passed through a diffraction grating. So remember a diffraction grating, and when a beam of white light is passed through a diffraction grating, the narrow slits split the white light into its constituent colors, with a white spot at the center of the pattern, and then with a continuous spectrum on both sides of the white spot at the center. So the white light is being split into its constituent wavelengths. And I'm saying because these colors overlap, we say that what is being formed is actually a continuous spectrum. But then a discharge tube, if we consider a discharge tube which is containing gas at low pressure, and the light coming from a discharge tube is again passed through a diffraction grating, then we may not experience or we may not observe exactly the same thing we have observed with white light from a tungsten filament. So a discharge tube looks like this. So think of a discharge tube. We have seen what happens when light is produced by a tungsten filament and is white light, and it is passed through a through a prism. It is split into 7 colors. To obtain fine details of the light, we pass it through a diffraction grating, and we notice that a continuous band of 7 colors would still be formed. Now let's think of a situation where light is produced in a discharge tube which has a gas at low pressure. When the gas is at low pressure, with gas at low pressure, it means the atoms are far from each other, and therefore they can behave as if they are isolated from each other. If gas is at high pressure, of course, the atoms therefore would be closer. But if gas is at low pressure, the atoms are going to be far from each other, and therefore a single atom may behave as if it is isolated from the other, which means an electron in an atom also behaves as if it is isolated from electrons in other atoms. And therefore, this light which is emitted in the discharge tube may have a different range of energies. Some light photons may have energy which is just enough to be absorbed by an electron to eject it or to move it to a certain energy level within the atom. A photon could be having high enough energy to promote an electron to a higher energy level. That photon will be absorbed. And what is the impact of absorbing that photon? So if light from a discharge tube is passed through a diffraction grating, we may not observe exactly what we observed with the tungsten filament. In fact, examination of this light when it goes through a diffraction grating shows that the emitted spectrum will no longer be continuous as we have seen in the previous example. But instead, what is observed is a continuous, actually, what is observed are bright lines on a dark background. Instead of us seeing the 7 continuous colors, instead we are seeing bright lines on a dark background as shown in this diagram here. So, examination of the light with a diffraction grating shows that the emitted spectrum is no longer continuous. Note now the difference between continuous spectrum and a non-continuous spectrum. So this spectrum now has bright lines on a darker background. Bright lines on a dark background. Because there are bright lines on a darker background, we still call it an emission spectrum. By this time, it's not going to be considered an emission. It is not going to be considered a continuous spectrum. So when a high potential difference is applied across the electrodes in a tube, in a discharge tube, light is going to be emitted. But when this light is passed through a diffraction grating, it's not going to be the 7 colors with a white central spot on the screen as we saw earlier on. I'm saying if this light is examined through a diffraction grating, the light shows that the emitted spectrum is no longer continuous, but it consists of a number of bright lines on a dark background. A number of bright lines on a dark background. Why do we have these lines? Now, this also takes us back to the failure of Rutherford's model. Why is it that when light from a discharge tube, which is passing through gas at low pressure, is passed through a diffraction grating, why do we see this dark line? Why do we see the dark lines or the bright lines on a darker background? These lines are going to be called the line spectra. So such lines are going to be called the line spectra. Such lines, which are dark lines on, bright lines on a darker background, are going to be called the line spectra. Of course, we shall also have dark lines on a bright background, but this time we have bright lines because you can see red, yellow, orange, green, blue, violet, indigo. So such a spectrum is now called a line spectrum as opposed to um, a continuous spectrum. So this one is a line spectrum. So it consists of a number of separate colors. Remember, each color being seen as the image of the slit in front of the source. Remember, we have passed the light into or through a diffraction grating. And when light goes through a diffraction grating, if the light from the source was simply a white light, when it is passed through a diffraction grating, we would see a continuous spectrum as we saw earlier on. But when light first goes through a gas at low pressure, when it is passed through a diffraction grating, this time we don't have a continuous spectrum. Instead, we have bright lines on a darker background. Of course, each line will be representing, or is going to be, each line is representing the color, and each color is seen as the image of the slit in front of the source. The wavelengths corresponding to the lines of the spectrum are characteristic of the gas, which is in the discharge tube. So the wavelength of these lines is not going to be the same if the gas in the discharge tube is, say, argon. The wavelength of the lines which are seen on the screen is characteristic of the gas which is in the discharge tube. So it depends on the gas which is in the discharge tube. Then how do we therefore explain this? So to explain how the line spectra are produced, we need to understand how electrons behave. How do electrons behave? Remember, we have earlier on said electrons only orbit around the nucleus in certain allowed orbits. And we say this prompted scientists to be able to calculate what are these certain allowed orbits. And therefore, if electrons exist in certain allowed orbits, why can't we say that electrons can only have certain specific energies? So, electrons in an atom can have only certain specific energies. These energies are the ones we are going to call the electron energy levels. So Bohr's model did not explain why the line spectra is produced or why the line spectra is observed. But Rutherford's model did not explain why the line spectra is also observed. But Neil Bohr's model tried to explain why the line spectra is observed or is produced when light which passes through a gas at low pressure is passed through a diffraction grating. So the line spectra which is produced can be explained by the behavior of the electrons. And according to Neil Bohr, if electrons occupy only certain allowed orbits, and while in those orbits they do not emit energy, then it means it makes sense for us to agree that electrons in an atom can only have certain or specific energies. And these energies of electrons are the ones we are going to call the electron energy levels of the atom. How do we represent these electron energy levels? So to represent these electron energy levels, or the energy levels, are going to be represented as a series of lines against a vertical scale of energy, as shown here. We shall represent the electron energy levels as a series of lines, horizontal lines, which are drawn against a vertical scale of energy. So each of these lines represents the energy which can be occupied, or the energy which an electron in an atom can have, depending on the atom, whether it is hydrogen. We shall concentrate on hydrogen. Remember, the lowest energy level, or the lowest energy for an electron in a hydrogen atom, where n was equal to 1, which we call the ground state, was minus 13.6 electron volts, which meant that the electron needs 13.6 electron volts to move to infinity, or to get completely free. So the levels, or the energy levels, have negative values because external energy has to be supplied to remove an electron from the atom. To move an electron to infinity, work must be done against the force of attraction between the electron and the nucleus. Therefore, in moving an electron against the attraction force, you are adding energy to the electron. Therefore, energy is gained as the electron is moved to infinity. Of course, to bring an electron closer to the nucleus, energy must be removed, or the electron loses energy, because naturally the force between the electron and the nucleus is attractive. So an electron with zero energy is completely free from the atom. Is completely free. Of course, infinity may not be a big distance, but a point where the electron does not experience an attractive force from the nucleus. So the electron in the hydrogen atom can have any of these energy values, but cannot have energies between them. So electrons within an atom have only specific energies. In other words, we say they occupy specific energy levels. An electron can have energy minus 13.6 electron volts, minus 3.4 electron volts, minus 1.5 electron volts. But an electron in an atom cannot have energies between, say, minus 3.4 and minus 1.5. So we say electrons only occupy specific energy levels, or the energy of the electrons in an atom is extremely discrete, just specific. So since an electron can only have specific energies, and according to Neil Bohr, it only gains or loses energy when there is a transition, then let's talk about these energy transitions as explained by Neil Bohr. So we have mentioned that normal electrons occupy the lowest energy levels available in an atom. That's when the atom is considered to be stable. So under these conditions, the atom and its electron are said to be in what we call the ground state. The ground state is the lowest energy state, or the lowest energy level of an atom. And in that state, the atom is always considered to be very stable. So normally electrons occupy the lowest energy levels available. So this figure, the figure below, is going to represent the hydrogen atom with its single electron in the lowest energy state. So naturally, the electron in the atom occupies the lowest energy level, which is minus 13.6 electron volts in the hydrogen atom. If the electron makes a transition to this energy level, which is minus 3.4 electron volts, and actually this is considered to be the first excited state. The first excited state. This is the ground state is called n equals to 1, and n equals to 2 is considered to be the first excited state. So the electron has made a transition. It can't make a transition from E1 to E2 without gaining energy. So it has gained a photon of energy. So when an electron gains a photon of energy, maybe this photon could be one of the wavelengths of the light produced in this charged tube. So the electron is promoted to a higher energy level. Just from the animation that we saw previously, this electron cannot stay here for long. This electron will have to move back to the ground state for the atom to be stable. The atom cannot exist in the unstable state for a long period of time or in the excited state for a long period of time. So as it moves back to the ground state, it emits this photon. So it emits this photon here. So moving to a higher energy level, the electron gains or absorbs a photon, it makes a transition to a higher energy level. And I said in that state, the hydrogen atom is in an excited state. And the atom cannot stay in an excited state for long. The electron will take a very short period of time and move back to the ground state, and that is going to be by emission of a photon which it had acquired previously. So what we are saying is that if an electron absorbs energy, it may be promoted to a higher energy level. We say that it can be excited from a lower to a higher energy level. This can be achieved in three ways. Which ways are these where the atom can be excited? One, any atom may collide with another atom. In the process of collision, the electron or an electron in one of the atoms gains energy to move to a higher energy level. Number two, an electron may gain energy from a photon. A photon of light incident on an atom may be absorbed by an electron and just enough to promote it to a higher energy level, which is actually one of the allowed energy levels. And also, an electron can absorb energy from another bombarding electron. And if that energy is just enough to promote the electron to another allowed energy state or another allowed energy level, that photon is going to be absorbed and the electron will be promoted to a higher energy level. But remember, the atom will be excited, the atom will not be stable. So the energy absorbed is exactly equal to the difference in the energy of the two levels. So an electron at negative 13.6 electron volts must absorb exactly the right amount of energy to promote it to negative 3.4 electron volts. If the energy obtained during the collision, or energy obtained from the photon, or energy obtained from the bombardment is not enough to promote the electron from this energy level to another specific energy level, that photon is not going to be absorbed by this electron. Remember, in the quantum, in the introduction or lesson 3 and 4, we mentioned that the interaction was a one-to-one. So the electron cannot absorb energy from two different photons. A specific photon interacts with an electron. It's a one-to-one interaction. So the energy absorbed is exactly equal to the difference in energy of these two allowed energy levels. So under these conditions, I've said the atom is described as being in an excited state, as we are going to see, or as we have seen in part B. So an excited atom is unstable. After a short time, we saw that the excited electron will return to the lower level or the ground state. To achieve this, the electron must lose energy, and it does so by emitting a photon of electromagnetic radiation, as we saw in part C. So that is what we mean by electron transition. Electron transition. So the energy, remember, is equivalent to the difference, or the energy is equal to the difference between two energy levels. Therefore, the energy of a photon, which is going to be absorbed to promote the electron to another allowed energy level, must be the difference between two energy levels. So for the electron left the ground state, that is E1, to be promoted to the first excited state, which is E2, the energy which is required to be promoted from this state to this state must be equivalent to the difference between the two energy levels. So only a photon whose energy is equal to the difference between the two energy levels can make that transition. So E1 is going to be the energy of the lower energy level, and E2 is the energy of the higher energy level. Of course, we know that H is the Planck's constant. You also recall that c equals to lambda times f, where c is the speed of light, which means f is going to be equal to c divided by lambda. Therefore, it means this equation here, we shall replace f in that equation, and f becomes c over lambda. So h over lambda is going to be the difference between the two energy levels. So I can tell even the wavelength of the photon, which is going to be to make that transition possible. The wavelength of the photon, which is going to make that transition possible. So this movement of an electron between energy levels is called electron transition. The movement of the electron between energy levels, that is going to be called electron transition. And of course, you will notice that the larger the energy of the transition, then the higher the frequency, because from this expression here, HF is equal to the difference in energy. So the higher the energy of the transition, the higher should be the frequency of the photon, either absorbed or the frequency of the photon which is emitted. And that is, of course, because frequency is inversely proportional to wavelength. It means the higher the frequency, the shorter the wavelength of the emitted radiation. So we shall distinguish between a downward transition and an upward transition. A downward transition means a photon is emitted by the electron, so it is an emission of a photon. And that is when an electron moves to the ground state, it emits a photon. Or when an electron moves to a lower energy level, it emits a photon. Or when an electron makes a transition to a lower energy level, it emits a photon. But if an electron makes a transition to a higher energy level, then it must absorb a photon. So downward transition results into emission of a photon. The atom can be raised to an excited state by the absorption of a photon, but the photon must have just the right energy corresponding to the difference in energy of the excited states in the initial state and the initial state. That's why we say the energy is equivalent to the difference between two energy levels. The energy is equivalent to the difference between the two energy levels. So in simple terms, therefore, a downward transition is going to be correspond to photon emission, and an upward transition is going to correspond to photon absorption. So this animation here demonstrates what happens when a photon arrives and is absorbed by an electron. We notice that an electron moves to a higher energy level. And when the electron loses the photon, the electron moves to a lower energy level, as demonstrated by this animation here. So a downward transition involves photon emission, and an upward transition involves photon absorption. Note that electron transition from one energy level to another requires absorption or emission of the photon, and these transitions are always represented by vertical arrows between energies. So remember, the energy levels are horizontal. The energy levels are horizontal as shown here, but then the transitions are going to always be represented by these vertical lines with arrows. For example, this arrow is showing transition from the first excited state to the ground state, transition from the second excited state to the ground state, transition from the second excited state to the first excited state. So this figure shows some possible transitions that may take place when electrons in an excited state, when an excited atom returns to lower energy levels. So sometimes the transitions will be pointing upwards, especially where a photon has been absorbed. When a photon has been absorbed, we expect an upward transition where the electron is promoted to a higher energy level. Okay, so one important thing I want people to notice is that each transition or each of the transition results in the emission of a photon with a particular wavelength. So every transition results in the emission of a photon of a particular wavelength or the absorption of a photon of a particular wavelength, because a photon has a specific amount of energy. and the electron requires a specific amount of energy to be promoted to a certain energy level, or when it moves from one energy level to another, it is going to give out a photon of a specific wavelength, specific energy, specific frequency. I want people to note carefully that energy levels become more closely spaced. You might have noticed that they become more closely spaced at the higher excited states. The energy levels become more closely spaced at the higher energy level states. That's why in the previous slides we have seen between the ground state and this first excited state, the next excited state, the energy levels get closer. They get closer. And the minimum energy required to remove an electron from the ground state of an atom is called ionization energy or the excitation energy. The minimum energy required to remove an electron from the ground state of an atom is going to be called the ionization energy or the excitation energy. For example, the ionization energy for hydrogen is about 13.6 electron volts, and this corresponds precisely to removing an electron from the lowest state, where E1 is a minus 13.6 electron volts, up to infinity where E is 0. So the energy required, which we call the ionization energy, is going to be 0 minus negative 13.6 electron volts, which is 13.6 electron volts. When an electron in the ground state is given 13.6 electron volts, it means its total energy will be 0 and the electron will get to infinity. So in that case, an atom would be called or would be said to be ionized or in an ionized state. The electron in a hydrogen atom can be in any one of the levels according to Bohr's theory, but like I said, it could never be between, say, in between, it could not have energy of negative 9.0 electron volts. It could never be in between, say, negative 9.0 electron volts. At room temperature, in most cases, nearly all hydrogen atoms are always in the ground state, that is, in the stable state. But at high temperatures, as temperatures increase or during electric discharge, when there are many collisions between the free electrons and atoms, many atoms can be in an excited state. So as temperatures increase, as a lot of electrons in the atoms gain energy due to increasing temperature, which makes the atoms to be in an excited state, which makes the atoms to be unstable. And of course, once in these excited states, an atom's electron can jump down to lower energy state. And in the process, if an electron gives out its energy, or if an electron moves to a lower energy state, it must give out a photon of energy. In the process, it must give out a photon, and this is according to Bohr's model, and that is the origin of the emission spectra of excited gases. So this is why we have the line spectra instead of the continuous spectra when a light from a discharge tube which has a gas at low pressure is passed through a diffraction grating. We have those lines because of electrons being excited and de-exciting, and note that this de-excitation may be random, as we shall see in our next lesson. So once in an excited state, an atom's electron can jump down to lower state and give off a photon of energy in that process. And that is the origin of the emission spectra of excited gases. In conclusion, I want people to note that since all elements have different energy levels, the energy differences or the difference in the energy levels are going to be unique to each element. Because elements have different energy levels, it means the differences in energy are going to be unique. For hydrogen, we have seen what happens. You may find that the ground state energy for other elements may not be minus 13.6 electron volts, as we saw with hydrogen. As a result, each element will produce different a different and characteristic line spectrum. We may not see the same bright lines in mercury, the same bright lines in argon. We may not see the same bright lines in any other element as compared to the ones we saw or the ones we could see with hydrogen. Therefore, spectra can be used to identify the presence of a particular element. This is why astronomers can look at light coming from stars and compare with light which is passed through maybe hydrogen or helium in the laboratory, and they conclude that in the stars there is helium or hydrogen because the spectral lines are in the same position as those ones produced in the laboratory. So, using the spectra, people can identify the presence of a particular material or a particular element. For example, the figure below shows the line spectra of mercury. So, if light is passed through any other substance and we see the same lines in the same positions, then we know that that substance could be having mercury in it. So different elements produce different characteristic lines, or different elements will produce different spectra. Different elements will produce different characteristic lines. Different elements will produce a different line spectra. The line spectra for mercury is not the same as line spectra for hydrogen. It's not the same as the line spectra for argon, and so on and so forth. So that is electron transition and introduction to line spectra. Let's see introduction to line let's see line spectra and absorption and lines and emission line spectra in our next lesson. Until next time, bye bye.
At 29 and I find myself wondering what did happen to the last 10. I ran away with my life, fast forward, never turn back again. It's kind of funny that the more we pass time, the more we need to set them rewind. And 19 was the year I had to leave you, but now I'm seeing all the signs. Is this really happening? I can't believe it's true. I'm just as surprised as you. Is this really happening? I can't be too sure, but one day I'll be yours again. Life lessons come one in a dozen. The other 11 give something from nothing. I sit here looking for an answer. Maybe the biggest question was in the last chapter. You gave me the soul I have today. Without you I never could have moved away. But now I see what you teach. I do believe I always should have stayed. Yeah. Is this really happening? I can't believe it's true. I'm just as surprised as you. Is this really happening? I can't be too sure, but one day I'll be yours again. One day I'll be yours. One day I'll be yours. I'll be yours. Life lessons come one in a dozen. The other 11 give something from nothing. Life lessons come one in a dozen. The other 11 give something from nothing. Life lessons come one in a dozen. The other 11 give something from nothing. Life changes just open the door. One thing certain.